needs a bowl. So I have a bowl with water. I have dish soap, and I have pepper. It can be pepper that's already grinded, meaning just the kind that you just shake out. This is just a pepper grinder, which means as I turn the bottom, it cuts up and makes fresh pepper. But it doesn't matter what it is. All right. So right now I got 34 people, and I'm gonna wait about 1 more minute or so. It also would be good to have, it would also be good to have a paper towel, so when you're finished, you can that you can just wipe your hands, because we're gonna use our hands. All right, so I see everyone's getting ready. Makisha, were you able to download Zoom onto the Chromebook?
No, I'm just using my phone.
Okay, how's that working?
It's fine. It's good.
Okay, all right, thank you. All right, if you have any kind of black seasoning or dark colored seasoning, that should be fine. So there's other kinds of like pepper that you might have in your cabinet. So, all right, so we're gonna go ahead and get started. I got 37, yay! Okay, so happy St. Patrick's Day. All right, are we all ready? Good? All right, so what we're gonna do is just for some fun, it's very important, obviously, that we're washing our hands right now. Red pepper might work, Lene. It might be a little too heavy. The idea is what we're gonna do, everybody, is you are going to start off with your bowl that you wanna have filled with water. So I filled mine so that when I put my finger down into the bowl, the water is a little bit higher than my fingernail, right? So that'd probably be like a couple centimeters. Okay. And what we're gonna be doing today is we're gonna do a little demonstration of why soap is so effective at helping us wash and clean, especially our hands during this time. So for this activity, we're going to take our bowl that should have water in it. All right, and we're gonna use pepper. I'm gonna grind my pepper grinder so I get little pieces of pepper. So you guys can go ahead and start shaking so that the pepper lands in your bowl with water. And you'll notice that a lot of the pepper is gonna stay floating on the top. And that's one of the ways that we know that water is so special. All right, and that's because water has something called high surface tension. So there's even animals that are able to run on water, like we have the Jesus or the basilisk lizard that's able to run across the surface of the water. There's insects called water striders, and they can run across water. They kind of look like a little spider. And the reason for that is water is super, super strong. The bonds between water are called polar bonds. And water is what we call hydrophilic. Water really wants to stick to itself, and that makes it so strong. And you guys learned about tension. Remember, tension's pulling, right? In opposite directions is a really strong force. And so that's one of the reasons why ships, for example, giant cargo ships can float on water, because water has high surface tension, okay? So when we look at our bowl and we put the pepper in, all right, so when we talk about the pepper, it's floating on top of the water right now because water's really strong and has really high surface tension, okay? What you're gonna do now is we're gonna demonstrate how effective soap is. So you're gonna take a finger and you're gonna take the dish soap, and you just wanna squeeze a tiny bit of dish soap so it's on the end of your finger, all right? And this is the fun part. So what we're gonna do is we're gonna take our finger, which should have dish soap on it, and now we're gonna touch the middle of our water with all of our floating peppers. So again, if you're not doing this at home, just watch me here on the video. So I take my finger and I touch the surface. Everyone should do this at home. All right, so what did we see happened? Oh, all went away.
All the pepper went aside. It means cleaning the bowl, I think.
The pepper went away from us.
Brian got scoop out.
Again,
Made a tornado.
All right, so all of the pepper should have shot away to the sides in every direction. And it's kind of hard because once you've done it once with your water,
already, and I'm just
it's
messing around.
No, don't. That's
which
how you make
is
a
doing
mess.
its job. It's
There's my
breaking up the
towel.
surface tension of the water. So,
And you're by my computer. I don't approve.
all right. So again, the idea is that soap chemically breaks up water surface tension. All right. So soap is doing its job because once you break the water surface tension, it helps to really to clean and get out dirt and grime and oil. And you can't do that if you have just water. So if you have like a greasy pan in your sink that you have to wash after dinner, if you don't use soap and you pour water on the grease, the water's really strong and it stays together and it'll literally just flow over your grease and your dirt. But when you add soap, it breaks up water surface tension. It breaks those polar molecules apart and it allows you to get through that barrier that the water is making to the dirt and the grime, and that helps to break it up and then remove it. So hopefully, right, the idea is that we know we just tested that this is why we wash our hands with soap, because chemically it's amazing and it works really well. All right, so those are allowed for today. So something fun and different, and you can show your siblings or people at home so you look like you know you're doing magic. But we are gonna go to Nearpod today, and we're gonna continue to talk about rocks. I'm gonna try to keep this one a little bit shorter today. But yesterday we were learning about relative dating of rocks and why that's important with something called the geologic time scale. All right, if some people have to leave, that's fine, but let's make sure that we're staying with me if you're here. So you're getting credit for being here. So thank you so much for being here. All right, so moving on, we should all be on Nearpod, so you guys can switch over so that you're looking at Nearpod. All right, and hopefully with enough time today, we'll get to a quizzes together. There's also some games or interaction that we'll have here on Nearpod. So everyone should see the Nearpod pulled up. Only got 4 people in there for now, so. All right, so I want to try to have all of our people from Zoom on. If you need to use the restroom, absolutely. Yes, if you want to go throw it away, you can throw it away. That's fine. We're just logging into Nearpod. I just put mine to the side, and then I had a paper towel to wipe off. I'm repping my Clovers for St. Patrick's Day. This is my Irish dance school. Represent. Yes, I like Andrew's garb. Excellent. Nice. All right, so I got 38 people in Zoom and I've only got 23 in Nearpod. So I posted the link for the Nearpod on Google Classroom. So if you haven't clicked on the Nearpod link yet to join, our code is UTZLA. So I got 25. All right, so today, if you have a question, the chat feature, I want you guys to get to talk to each other because I think that I'm sure you guys miss each other. But also let's try to keep this professional. So if you have questions, you can use this chat feature to ask me, and then as a class, we can talk about it together. So I want the chat to stay based on school, if you don't mind. Thank you. Okay, yeah, well, that's what we got to do. I've got Marku. Thank you for joining us, Marku. I got Ian and Samira. It looks like your links went bad, so maybe just refresh it. Oh, never mind. I can see it. All right. So everyone should be able to see the code on my screen right now. So if you're not in, you can join us later. All right, Noah, Andrew, people in the chat, let's just focus on this. All right, let's move on. I say that and then I can't with all of these things up on my screen. All right, there we go. All right, next slide. All right, so everyone should be on Nearpod. So if you can have your Nearpod pulled up, and then I'm kind of just talking in the background here. We'll go through these slides together. So for our first, for our focus today, we've been talking about relative dating of rocks. And the reason why we're talking about that is that for a really long time, we had no idea how old this planet was. We didn't have any way to know that. So when it came to relative dating, the law of superposition was all we had. We knew that layers that were underneath or lower, closer to Earth's surface, right, deeper layers had to be older. They had to be laid down first, right? Just like we talked about how you make a sandwich and stack your layers. We know that layers of rock have been stacked over time in chronological order, which kind of allowed us to see how the history of Earth has changed, right? What kind of plants, what kind of animals have been around. But today now we're going to answer the question that a lot of you have had, which is, all right, but how do we actually know how old things are? And that's called absolute dating. That involves a little bit of chemistry, but it's relatively simple, and it's allowed us to be able to get an exact date for how old things are, almost down to the month if it's been recent enough in history. All right, so moving on. I'm going to skip this slide. This just kind of covers what we're going to talk about today. We've already talked about the law of superposition yesterday. Oldest layer at the bottom, youngest layer at the top. And today we're moving on to talk about relative dating, which is what superposition is doing. And we're now talking about absolute dating, how we figure out exactly how old things are. 400 million years old. How did we know that? Well, that's with something called radioactive dating. All right, so our warm-up question says, how do scientists use the physical world to deduce the history of planet Earth? In other words, how do we figure out how old, right, or what do we learn from the physical world to figure out our history? So physically, what do we look at that gives us this information? So again, we'll talk about the difference between absolute and relative dating, figuring out how exactly we figured out the age of objects. All right. So again, we're going to learn about absolute dating today and figuring out that thing called radioactive dating of how we figure out exactly how old it is. All right, and our first question, it says, what do you already know about how geologists determine the age of a rock formation? So this is from yesterday. So yesterday we watched a few videos and we discussed and did an activity. How do we know how old or the age of rock formations? Nice job, Blaze. Nice job, Anna, Alice, nice job. Yes, Hadrian, good job. So we're, Miles, nice. All right, some of us I don't think completed. Oh, there we go. All right. The deeper the rock is, the older it is. The fossil, Sharika said, right, nice job, Lene, excellent, Riley, awesome, Avante, killing it. All right, so yeah, so the fossil thing is important because yesterday we talked about these things called index fossils, right? And we know that they only lived at a certain period of time. So if you have one, you know the rock you're holding or the mountain or the landform that you got this fossil out of, you know has to be as old as that fossil is. Meaning, we talked about the trilobite fossils yesterday. Those only lived between 250 million years ago and 500 million years ago. That's a long range, or that's a wide, span of time. But still, we know they didn't live after 250 million years ago. So if you have a rock that has it in it, you know that you're looking at a landform that is at least 250 million years old, right? So very good. All right, let's make sure we finish them before we submit. Okay, very good. I got a few more coming in. Yes, so superposition, and that's just a fancy way of saying that oldest layers are at the bottom, the youngest are at the top. When we put them in order, we can figure out evolution, figure out how life has changed on this planet. Very good. All right. How does understanding the history of Earth help us today? So we talked a little bit about this yesterday, but we study history for really important reasons. And I'd like you to try to give us at least one reason why it's important to study the history of Earth. How can that help us? So I'm going to ask because we're going to talk about radioactive dating today. Yes. So certain types of radiation could kill you. Okay. When we talk about radioactive dating, it sounds really scary, but all it means is that there's unstable things called isotopes, meaning atoms all over the place they're an isotope, which means they have more neutrons or they have less neutrons than they're supposed to, meaning in their balanced ratio. And there is a mathematical equation for exactly how long it takes every one of those types of atoms to decay. All right. And there's different ones we look for. One of them is carbon. So remember, every single living thing is made of carbon, right? If you burn dead stuff, you release carbon dioxide, right? You and I breathe in, right? Oxygen, and then we eat sugar, which has glucose, which means it's made of carbon, and our body makes and builds tissue with carbon. So every living thing has carbon in it. So when we look at an organism, meaning a fossil, we can count its carbon atoms, and we can find how old it is by figuring out how far along their carbon atoms have decayed. There's a type of radioactive carbon called C14, carbon 14, and it just means that it has 14 neutrons. Or its mass is 14, and then it'll tell us that it has 8 neutrons. So the idea is that if you can figure out how many of those C14 atoms have decayed, you can figure out how long ago the carbon got stuck in the animal, which means the last time the animal was alive, if that makes sense. I don't want to overwhelm you with that yet, but the point is that there are some radioactive isotopes around and in our body, like C14, and they don't cause us harmful radiation. They're radioactive, but on a level that doesn't really influence or harm us. All right, so really good question. All right, nice job. So again, how does understanding the history of Earth help us today? It helps us by telling us what's happened in the past and how we can expect, right, what might happen in the future. So a really big one is talking about carbon dioxide. We know that, yes, we can also prepare for natural disasters. I'm reading all of your answers now, so great job. Understanding the past allows us to prepare for the future. So when we talk about how we know our planet can change in regards to climate, it's happened many times before. So when we talk about climate change, unfortunately, people that haven't maybe studied or paid attention in science class don't realize, like, we've gone through periods of global climate change many times in Earth's history. We've had ice ages, right? Right now, we're the opposite of an ice age. We're in a period of warming. This has happened several times, and we know and can study what happens from rocks and fossils when some of these levels can get really high. So this is why we have those conversations. Nice job. Making sure history doesn't repeat itself. Great job. All right. How to date a planet. So this is going to get into radioactive dating. So there are different elements that are radioactive, and they have isotopes that we can look at, and we know exactly how long it should take them to decay. And if we see how far along they are in that process, we can figure out exactly how many years old, right, that sample is, including for a planet. So we were talking about last week, I was passing around a meteorite sample to some of you guys, and we were talking about meteorites, and I said, how do you know you have a meteorite? And the answer is the meteorite should be older than our planet, because it formed before our planet did. Because when our star exploded, when our sun exploded, it made a bunch of matter go spraying outward, and those are meteorites, right? And those formed before Earth did, right? Earth took time, right? You had all this matter collecting and coalescing. So, all right, so moving on. Everyone is going to watch this video about how to date a planet. You guys are all able to watch these videos at your own pace. I'm going to mute mine so you guys can now all be watching your video on your own. And then when you're finished, just shoot me a chat and we will move on. All right, so a lot of us have finished. So at the end, they said these rocks are older than dirt, which is a common saying that people say when they say they're old. They're like, I'm older than dirt. But you know that dirt isn't, you know that dirt is actually made from organic life, right? Dirt comes out of worms, it comes out of leaves that have fallen apart, decayed, bacteria and fungi. And dirt is organic, right? So rocks, not living, right, are going to be older than dirt. So that was the joke. All right, so moving on to our next page. So explain why it's difficult to determine the age of our planet. So we just finished a whole lesson where we talked about plate tectonics. We talked about Earth and how we know the constant activity it has, volcanoes, earthquakes, seafloor spreading, right? All these things. Don't eat dirt, please. If Earth's surface is constantly changing, that poses a problem for us. All right. All right, so Christina said because when rocks change, they can lose all of their evidence. It tells us how old they are, right? So everyone, your answers should have included something about what you've learned with the rock cycle. It's called a cycle because rocks are always usually changing, right? If they get melted, that erases whatever record we would have had about how old it was before, right? So igneous rocks, done. Sedimentary rocks, it depends. Sometimes you can get something there, but as soon as they get metamorphosized, that heat and pressure can destroy or change, alter, basically starting the clock over again. So yes, very good. Alice, nice job. Because Earth's always changing, renewing itself. The oldest rocks can get destroyed. So here's a good question. So where would the oldest rocks be found on Earth? On land or in the ocean? We'll do that random thing where I scroll and unmute someone's so they can give us the answer. Yay! All right, where would the oldest rocks be found? On land or in the ocean? Braylee. Braylee.
Yeah. Yeah.
Where would the oldest rocks be found? In the ocean,
ocean.
or on land?
In the ocean.
All right, so I know this is a trick question because you have to remember what happens in the ocean. What happens when old crust on the ocean floor gets to a subduction boundary?
Like
So remember, at a subduction boundary, an old piece of ocean floor is going to go where?
subduction happens.
It goes down, right? It goes back into the mantle. So our oceans are
Yeah.
actually a lot newer because the rock is constantly at the bottom. The seafloor gets subducted right over again.
Yeah.
So when we talk about, I'm going to answer the Pearson question in a second. So when we talk about rocks, we know that they have to be on land because remember that land is constantly like floating, if you will, and Pangea is broken up. Our continents are going to realign again on the other side of the world, but it's almost like our continents have been floating. So your oldest rocks are going to be on land where they're not at risk of getting subducted back. So Australia has been separated from most of the rest of the world for a while. So that's why it makes sense we found the oldest rock in Australia because it hasn't been collided with or had any significant changes done to it. All right. All right. Whoever's drawing, I need them to stop so I can go back and see who's doing that later. So please don't do that. All right. So moving on, we are going to go on to our next question. I did assign something on Pearson and I just asked that it be done by the end of the week. You don't have to do it right now or today, but I had it due by Friday the 20th. And that was just, again, relative aging with the layers. All right. But we're going to move on to our next activity. So on Pearson, we've got about 10 or 15 minutes left. So stay with me. It says extreme planet makeover. As we learned from the video, natural forces that take place on Earth cause the surface of our planet to continuously reshape itself. This makes it difficult to determine the age of Earth as it destroys this evidence, making it difficult for us to estimate. It says, what are some natural forces that cause Earth to be constantly reshaped and renewed? It says think, pair, share. We can't really do that, but what are some of the forces? So some of the things that we can say would be what basically breaks apart and makes sediments? Weathering. Breaks it, erosion takes it when the motion stops. Right, so you know that wind, water, right, are all ways that rocks can get weathered. We also have collision, right, uplift of mountains, so at convergent boundaries, the pressing of our plates together can crush or break up rock in that way, making it hard to find the older pieces. Nice job. All right, nice job, people. I got 65%. Braley, excellent job. Billiam, good work. Let's keep our regular names. Willie, thank you. Yeah, that's true. Gravity, once stuff gets broken up, it'll fall. Nice. Wind, water, weathering, yep. Avante, Hadra, Mary, where are you at? Oh, I see. There's multiple of you. Okay. All right. Nice work, everyone. All right, so for this next one, we're going to talk about, I'm going to skip a little bit on relative dating. Hopefully at this point, we all know what relative dating is. It's saying something's older than something else. You don't know how old it actually is, but again, the oldest layers are at the bottom, the youngest layers are at the top, and that would be relative dating. It doesn't let us know exactly how old it is. So in this next slide, once again, younger layers at the top, older ones are at the bottom. That lets us know relative age. But today we're learning about something called absolute dating. So this is how we figure out exactly how old they are by a process called radioactive dating. This specific absolute age talks about, this next slide talks about what I mentioned on Friday, which is that you can determine the exact age of other objects in some other ways. So for example, trees, this is called dendrochronology. You can figure out how old a tree is by counting its rings. So just like we made a cross section of our Snickers bar, you make a cross section of a tree and you look at the side, you can count how many rings there are. The number of rings would be the same as the number of years the tree has been alive, which is pretty amazing. It says bigger rings form when there's abundant moisture, meaning lots of rain and nutrients. You would get a smaller ring or a thin ring when there's a period of drought where there's no water. Oops, sorry. So there's a picture of tree rings here. So if you actually counted each of them, you'd be able to figure out exactly how old it is. So again, that's called dendrochronology. And actually, when we talk about time, when we look at super old trees, so the redwood forest in California, it's a national park, those trees are over 1,000 years old. So when we want to know what's been going on in history and we have something like a tree around that's still alive, we can take a look at what's happened. Yes, I realize you're like, oh my gosh, you're going to cut the tree down. A lot of times those trees will fall, and then if they've already fallen over, then we can cut them and find and count back the years and see when there was major droughts or fires or lots of rain. So it's pretty incredible if we have something like that to compare to. All right, so let's do an activity based on that. It says your family's just cut down a tree in your backyard. Look at the cross section of the tree below and count the different colored rings. How old was the tree when it was cut down? The little orange band that's there, it doesn't count that are in between them. They're showing you they're different. Very good. So our answer should be somewhere around 15. Yes. Nice job. When you're looking at it, you can see some of the bands are really thick. So if you look 1, 2, 3, 4, the 5th and 6th bands, right, from the middle of the tree. So if you start from the core and then count all the way to the outer edge, band 5 is the thickest band. That shows you that they got a ton of rain that year. Again, on a small scale, this isn't as important, but when we talk about Earth's history, you got 1,000-year-old tree, you just got 1,000-year record of what's been going on in that region and that climate for the last 1,000 years, thanks to trees. So it's pretty cool. Another way in science that we can kind of piece together the puzzle of time. Nice. Yes. Lakaya. Nice. Gianna. Woo. Yeah. Nice job. Yes, Ian. Good job. Yep, so our answer should be around 15. Good job. All right, nice. All right, most of us have answered. I'm going to go ahead and move on just because I think some people might have had to step out for the bathroom or whatever, so I'm going to keep going. All right, so this part is where it's a little bit more difficult. So we're going to talk about something called carbon dating. So again, we talked about C14, and this is how we figure out exactly how old something is. I'm going to warn you, it's going to seem complicated at the beginning, but ask questions in the chat if you don't understand. But let's read this together. So I'm going to read out loud, and I want you to read your screen in the text as I read out loud. I want you to follow along with me. So carbon dating. Living things use a special kind of carbon in their cells called C14, which is simply a carbon atom that's a little bit heavier than it's supposed to be for a regular carbon atom. When something dies, the C14 will begin to decay into a special kind of nitrogen called nitrogen 14. Every 5,730 years, half of the C14 in an organism will decay into N14, nitrogen 14. This is known as a half-life. By looking at what percentage of C14 is in a fossil, scientists can figure out the age of the organism when it died. Okay, so next slide shows you a chart. So on the y-axis, it goes from 0 to 100. So look at the y-axis, 0 to 100, and it's at the top would be 100, meaning the thing just died. It's got all of the C14 in it because it literally just died. A half-life is when 50% of the C14 is gone, okay? So notice that the red is showing you one half-life, and it says that one half-life of C14 takes 5,730 years. Can you guys see my cursor on the chart? Yeah? Okay, thank you. All right, so again, stay with me. So it takes 5,730 years for 50% of the carbon 14 to go away, okay? And then look again at the x-axis. It takes 11,460 years for 25% of the carbon 14 to remain. Meaning if 75% of the C14 is gone, that means 2 half-lives have passed, which means that thing died at least 11,460 years ago. I know you're like, what? But that's really incredible. There's like this simple math equation that we found out that you can use to figure out exactly how old stuff is. Yeah. Okay. So again, looking at the chart, this goes on, but notice that once we get past for carbon, look at our x-axis. It shows 1 half-life has passed. That's 5,730 years. 2 half-lives, 11,460. 3 half-lives would be 17,190. Notice that you've got fewer and fewer and fewer left of the sample, which just shows us that once we get past 28,000, so like 30,000 years, there won't be enough carbon left in something to figure it out. So carbon, we can only use for stuff that's died within the last 30,000 years. Okay, if something's older than 30,000 years old, we can't use carbon, but there's other things you can use. Like the video said, we can use uranium. Okay, a little bit harder to do, but we can do it. All right, so moving on to the next chart. Okay, so here we are, uranium. Carbon dating is very useful for things that died within the last thousands of years, but for artifacts that are older than 30,000, carbon dating is ineffective. You can't possibly count them out and find it all. So it says instead of looking at carbon 14, scientists can look at uranium instead. Over time, uranium will decay into lead. This takes a lot longer. The half-life of uranium is 4.5 million years. And that means that if we can count the uranium in a sample, it'll tell us how old it is for things that are even as old as meteorites or our solar system. Okay, I know I'm losing you. We have one more activity left. Okay, so this last page is showing you, if you look on the x-axis this time, this would be the chart for uranium. So each one of the vertical bars here is showing you a half-life, because a half-life for uranium is 4.5 right, millions of years. So if you take a look here at 50%, right, you can see how much is left. Yeah, uranium's half-life is 4.5 million years. So again, we can date a meteorite using uranium. And again, that's anything that is older than 30,000. You can't use carbon. That's also one of the reasons why we can't bring back the dinosaurs, because their DNA is too far removed. All right. I think I kind of want to do this one activity, and then I'm going to leave it here for today. All right, so this is our one last question that we're going to do together today. If you have any other questions, you're like, this is a little confusing, please go back and watch the videos. I also have one more that we're going to start with tomorrow about absolute dating. But this final question for today says, archaeologists have discovered a mummified corpse, ooh, a mummy, and they want to know how long ago she died. They determined that there's 25% of C14 in her body left, which means 75% is gone. So if you look at your chart and they told you she only has 25% of her C14, that means your mummy has to be how old? And for some of you that are like, okay, is it always that perfect? No, but this chart you can use for, as long as you know how much C14 there is compared to how much there was before, which again is pretty easy to do, then you can use this chart to figure out how old the thing is. Almost down to the month for carbon. All right, so again, the question is asking, yes, Andrew, yeah, good. Yes, Alice, you got it. Okay, so archaeologists discovered this mummy. They determined there's 25% left. If you look at the 25% on your y-axis and you run across on your y-axis to find how many years have passed, the answer's on your chart that it's 11,460. If she only has 25% of her carbon left, that means 2 half-lives have passed. It means 75% of it's gone, meaning she died at exactly 11,460 years ago. And it's not always that perfect in like real science, meaning there might be 37% of someone's carbon left, but you just use the curve on the chart and to find your answer for how long ago this specimen would have died. Yeah. So when scientists are like, this fossil is 256 million years old, and you're like, how on earth would someone know that? This is how they know. So they're not making it up, promise. Some of you are like, okay. Yeah. Nice job, everybody. All right, if you have any other further questions, please shoot me a message in the chat or send me an email. I did post that Pearson activity, and I made the due date Friday just because some people have to help siblings or go to the bathroom. So I didn't want to make that a strict due date. But again, if you guys need anything, have questions about anything, shoot me a message. But I hope you have a great day. Happy St. Patrick's Day. Do a little jig. Something. Go find a lucky 4-leaf clover. You can find them. All right, how do I change? Stop share. Okay. All right, bye everybody.
Bye, Miss Ryan.
Bye, thank you.
Bye.
Have a good day.
Adios.
Medusa.
I
Have a good day, Miss Ryan.
You too.
said,
Thank you,
bye.
everybody.
I said, but.
What did you get? You got nothing? No.
Sorry, man.